right, now that we've taken a look at some basic probabilities and odds, we're going to take a look at some other ways of looking at events happening, and those are combinations and permutations. But before we get started on what they look like and what they represent and some formulas, we need to first go over a notation that you may or may not be familiar with. And it's the definition of what's called a factorial. Factorial. And the symbol for a factorial is an exclamation point. So you'll see it this way. A natural number with an exclamation point. So we're not just yelling. What this means is, this means the product of all natural numbers less than or equal to whatever natural number I give you. And if you remember, natural numbers are the counting numbers. Natural numbers are 1, 2, 3, 4, etc. So the smallest natural number is the number 1. So for example, if I ask you to calculate 5 factorial, well, we need to take the product, we need to multiply all the natural numbers less than or equal to 5, so including 5. So that would be 5 times 4 times 3 times 2 times 1. Okay, so the smallest natural number is 1. And if I do that multiplication, 5 times 4 is 20, 20 times 6, we get 120. Okay, so I think you've got the idea there on what factorial means. Now let's say I ask you to simplify 5 factorial divided by 3 factorial. Well, we need to expand it. So this first time I'm going to expand the whole thing out, and then we'll take a look at some other shortcut ways of doing some of the expansion. So by definition, this would be 5 times all the natural numbers less than 5, divided by 3 times all the natural numbers less than 3. So I always try to line them up underneath each other because then I can start reducing. 1 divided by 1 is 1. 2 divided by 2 is 2. 3 divided by 3 is 3. So I've reduced those common factors, and I'm left with the product of 5 times 4, or I'm left with 20. Okay? Now let's say I give you something a little bit larger. Let's say we look at 10 factorial divided by 8 factorial. You know, or this could have been 70 factorial. But you may look at this and you might go, well, I know 10 factorial is 10 times 9 times 8 times 7 times 6, 5, 4, 3, 2, 1. And this is also 8 times 7 times 6, 5, 4, 3, 2, 1. So what I'm going to start doing is I'm going to start expanding this. This is the same as 10 times 9 times 8 factorial over 8 factorial. So I don't have to expand it all the way down to 1 unless it's easier for you to do that. And then now 8, 7, 6, 5, 4, 3, 2, 1 and the product of 8, 7, 6, 5, 4, 3, 2, 1, those are all going to reduce. And so this would end up with 90. Okay? Now, one thing you do not want to do not reduce the 10 and the 8 first. If you had reduced this to 5 over 4, 5 factorial over 4 factorial is not 90. So do not reduce first. You can only reduce factors, and factors are the things, terms, expressions that you multiply together. All right, so expand and then reduce. Remember, factors are what you multiply together. Terms are what you add and subtract together. All right, now what we want to do is let's take a look at permutations and combinations. So I'm going to tell you what they both are by definition, and then we'll practice some, and then I will also give you their formulas. Okay, so in fact, I think I might kind of give you their formulas as we go. All right, so what we want to do is, when we look at a factorial, sometimes you'll also hear this referred to as the fundamental counting principle. All right, so you may hear that sometimes, and I'll show you what I mean with some examples. All right, let's take a look at the definition of a permutation. Okay, it's elements in a set, but they have to be in a certain order. Elements in a set which are in a certain order. I'm going to actually highlight that. Okay, so a permutation, order matters. Examples of order. Let's say you are running a race. Well, if you're running a race, you probably have somebody that comes in first, second, third place. So order matters. That would be a permutation. If you are putting books in alphabetical order, well, A has to come before B, before C, etc. So order matters. If I say, let's form a committee, and we need to have a president, a vice president, a secretary, and a treasurer. So we're going to form a committee or a club, but because we have those specific roles, orders matters. Versus a combination where order does not matter. So we would have elements in a set where order does not matter. All right, so you might say, I'm making a pizza and I want to put the toppings on the pizza. So does it really matter if you put the pepperoni down before you put the onions and the... No, you just need to put them down there. Or I have a classroom of 20 students and I want to break people into groups of 4. Well, I just need to randomly put groups of 4, so order doesn't matter. That would be a combination. And I know sometimes it gets confusing because if we think of a combination lock, order matters. So a combination lock is actually a permutation. Okay. So here are some examples. Of a permutation. And I also want you to think about the idea of the fundamental counting principle. I mentioned that a little bit before. Okay, let's do this one. Let's talk about making an ice cream cone. So we want to arrange some ice cream flavors. So let's find the number of permutations of arranging the ice cream flavors on a cone given chocolate, vanilla, strawberry. All right, now this is using the fundamental counting principle, which, remember, this is also known as the fundamental Counting principle. I think I got the wrong principle. I think it's PLE. Okay, I'm sorry about that if the spelling's wrong. So let's do this. Let's find the number of permutations of arranging ice cream flavors on a cone. And we're going to take a look at 3 flavors: chocolate, vanilla, and strawberry. Using chocolate, vanilla, and strawberry ice cream. Now, some may say, well, order doesn't really matter, which can be very true, but in this case, if I annotate, I notice that I told you we're looking for permutations. So if I tell you it's a permutation, then there's a certain order. So I'm going to do this with a tree diagram first, and then I'm going to do it in kind of listing a way. All right, so let's say we do a tree diagram. Well, our first scoop, we have 3 choices. We either have chocolate, vanilla, or strawberry. Okay? And then we have to then go, all right, well, for the second scoop, so right now we have 1, 2, 3 possible scoops. So right now we have 3 ways that this can happen. Now, if order matters and the first scoop is chocolate, well then that means our second scoop can only be vanilla or strawberry. So we only have 2 choices. If our first scoop is vanilla, then we only have 2 possible outcomes for the second scoop. The first one's vanilla, the other second scoop might be chocolate or strawberry. If the first scoop is strawberry, then we only have 2 choices of chocolate or vanilla. So we only have 2 ways we can have the second scoop, because it depends on the first scoop. So order matters. Since it depends on chocolate, there's only 2 other choices. If it depends on vanilla, there's only 2 other choices. Same with strawberry. So in this case, there's only 2 ways to have a second scoop. And then following that same idea, this last scoop, well, if we have chocolate for the first one, and then we have vanilla for the second one, we only have 1 way, and that would have to be strawberry. If we have chocolate for the first scoop, followed by strawberry for the second scoop, then we only have 1 way, which would be vanilla. Now you can keep going. If we have vanilla, then chocolate, the only choice left is strawberry. If we have vanilla, then strawberry, the only choice left is chocolate. So you can see how this pans out. And in each case, there's only 1 way we can have a third scoop, because order mattered leading up to that scoop. So if you notice, this ends up being 3 factorial. This happens, I need all of them. I need a first scoop and a second scoop and a third scoop. I need to have all of them in order to have 3 scoops of ice cream. So because it's an and, this is 3 times 2 times 1, which you'll notice is 3 factorial. So there are 6 permutations. So if you ever have a factorial like this, where order matters, this is called the fundamental counting principle. Okay? Now, somebody else may have organized it differently. I'm going to look at that same example, and I'm going to organize it without a tree. Same example, let's just set it up again. So I'm not going to write it all over again. I'm just going to set it up, here I'll do this in blue. So if I set it up again, let's say instead of doing a tree diagram, I decide to just sort of create a list. I'm a very visual person. So one thing you could do is say, all right, I'm going to have 3 flavors of ice cream. So I'm going to call, here's my first flavor, here's my second flavor, here's my third flavor. So here's the first scoop. And the second scoop. And the third scoop. So you have 3 scoops of ice cream sitting here. Well, how many ways can you first scoop for the first scoop? Well, I have 3 ways. Well, now that I've used up one, for the second scoop, I only have 2 choices left. And for the third scoop, I only have 1 choice left. And again, you could have listed them as chocolate, vanilla, strawberry, and then would depend on what you had after that. Okay? So once again, we get 3 times 2 times 1, so we get 6 ways. So let's try another example of that type of problem. Okay. So it really gets you thinking sometimes with Baskin-Robbins, also known as in the day 31 flavors, if you have 31 flavors of ice cream to choose from. Okay. So here we go. Here's the second example. How many permutations are there for placing 6 books alphabetically by author on a shelf? How many permutations are there for placing 6 books alphabetical by author on a shelf? And of course you can draw a tree diagram. You could have your first book and then your second book and then your third book, etc. I'm going to choose to list them. So for a couple of things, first of all, I notice it says permutations. And I notice I have 6 books. So I'm going to go, okay, I have book number 1 and book number 2 and book number 3 and book number 4 and book number 5 and book number 6. And I have to have all of them together if I'm going to have all 6. So I'm just going to call this book number 1, number 2, book number 3, book number 4, book number 5, book number 6. Okay? So let's think about that now. All right, so you're going to start. Well, if you have 6 books, how many ways could you have the first book on the shelf? Well, we have, because if I have 6 books, think of it this way. I have book A, B, C, D, E, and F. I have 6 books. Here are my books. All right, so how many of them do you have to choose from to go first? Well, we have all 6 of them. Now that one book is placed, how many ways do we have, or how many books do we have to choose from to go second in place? Well, we have 5 books left. Once that book is placed, well, we only have 4 choices left. Once that book is placed alphabetically, now we only have 3 choices left. And then we have 2 choices. And by the time we've placed the 5 books, there's only 1 book left in our hand. And so you'll notice again, fundamental counting principle. This ends up being 6 factorial, which is, well, we left off with 5 factorial was 120. 120 times 6 should be 600, 720. So we have 720 ways to put those on the shelf. Okay? Okay, now, all right, so I think that's kind of gives you an idea. Now we do have a formula for permutation. Let's say, because this time we used every single item. Let's say it's like that 31 flavors ice cream problem. Let's say you have 31 flavors to choose from, and you only want an ice cream cone with 3 flavors. So although you have an entire set, an entire sample space to choose from, you only want a certain number. So here, let's take a look at our formula now. Okay. For the number of permutations or objects that are chosen from a set. So the number of permutations of R objects, and R is just a variable of, here I'll switch colors so that we, of R objects chosen from a set of N objects. N represents a natural number, a counting number, because we're counting how many things. So a way we might actually read this is we would say the permutations out of N objects chosen are at a time. Okay? So we have a formula for that. And I like to have people just read left to right. We want the permutation of N objects chosen are at a time. So if you want to write that in words, that might help. Permutation of N objects chosen are at a time. And if I read left to right, this is N factorial divided by the difference of N minus R factorial. So let's just calculate first. Let's just practice this calculation. So if we just practice this formula, I would like you to find the permutation of 8 items chosen 3 at a time. So how many ways can you have 8 items and you only pick 3 at a time? So let's say you have 8 jelly beans and you want to grab 3 jelly beans at a time. Well, there's a lot of different ways you can get those jelly beans. So if I follow this formula, 8 objects chosen 3 at a time. So this would be 8 factorial divided by 8 minus 3 factorial. So this would be 8 factorial over 5 factorial. So this would be 8 times 7 times 6 times 5, 4, 3, 2, 1. And this is divided by 5, 4, 3, 2, 1. And if we do this, 5 factorial reduces with 5 factorial. I should have come up with the solution ahead of time. So 8 times 7 times 6 is 336. So the permutation of 8 objects chosen 3 at a time is 336 possible ways. Okay. Now let me show you another way we could also do this. Let's do one with words. So you may go, okay, let me figure this one out. Let's say you are planting hedge or bushes in your front yard, and you know you want to go from left to right, and you want them in a certain order, maybe a height order, something like that. So let's say we do the following. How many ways can 4 bushes be planted in a row given 7 plants to choose from? In how many ways can 4 bushes be planted in a row given 7 plants to choose from? Okay. All right, so what we need to do is we need to think about what's our total number, our total sample space, and then how many are we trying to select out of there. So in this case, this would be the permutation of 7, choose 4. And now if I follow the equation, that gives me a 7 factorial over 7 minus 4 factorial. So this is 7 factorial over 3 factorial. And please set it up for me so I can see where you got it from. And again, 7 factorial is 7 times 6 times 5, all the natural numbers less than it. And I'm going to stop when I get to 3, 2, 1, because that's exactly what would be in the denominator. 3 times 2 times 1. And so now, if I reduce 3 times 2 times 1, I am left with 840 possible ways that you could arrange those plants. Okay? Now, we can also, I want to take a look at, a real classic is arranging letters in a word to create other arrangements. Not necessarily words, but other arrangements of letters. So I'm going to do 2 examples. One where you don't have any letters repeating, and another example where you do have letters repeating. So how many ways can the letters in the word today be arranged? This actually kind of goes back to the fundamental counting principle, because I could start with, well, let's think about these letters. I have the letter T, O, D, A, and Y. So I have a total of 5 letters. Okay, well, if I'm going to arrange them, and let's arrange them 3 at a time. I suppose I should have done that. Be arranged 3 at a time. So maybe I take the T-O-D, or TOA, or TOY. And you can imagine this is going to keep going. TDO, TDA, TDY. We're not asking how many words, we're just wanting to arrange the letters. So in this case, since I've got a parameter on it, and I've said 3 at a time, we need to use this formula for permutation. If I had just said how many ways can they be arranged, well, we would have had 5 times 4 times 3 times 2 times 1. But because I gave you 3 at a time, now I'm looking at a permutation of 5 letters chosen 3 at a time. So that gives us 5 factorial over the difference of 5 and 3 factorial. And so that gives us a 5, 4, 3, I'm just going to go all the way down to 1. If I reduce the 2 factorials, I am left with the permutation of 5 choose 3 at a time would be 60. Okay? So hopefully that helps a little bit. All right? So notice in this case, here's a big thing, an important fact to notice. Notice there are no repeating letters. No letters repeat. So that's a big piece of information to pay attention to. We didn't end up counting a letter twice because it repeated. Okay. Excuse me. So we're going to do the same type of example, but this time we're going to do the same type, and I think I can do it with an example instead of writing it all out. We're going to do an example of arranging letters again, but we're going to have repeat letters this time. And just like we did when we were working with our mutually exclusive or not mutually exclusive, if we have repeats, we have an overlap. So we may have to keep that in mind. Now, permutations are all about multiplication here. All right, so let's do the same idea. How many ways can you arrange letters? Let's just start with in the word bookroom. How many ways can the letters in the word bookroom be arranged? Now this time I'm just arranging them. So I'm not taking 2 at a time. I'm not taking 3 at a time. I'm just arranging them. I'm just moving them around. So the first thing I would do is I would figure out, well, how many letters or how many spaces are there? Because I want to take and I want to rearrange these. And I want to know how many ways I can rearrange them. So first of all, I'm going to notice that I have 8 slots or 8 letters that I'm rearranging. All right, so if you think about that for the visual person, I have 1, 2, 3, 4, 5, 6, 7, 8 ways, and I have 8 letters I have to fill in. So for the very first letter, I have how many to choose from? Do I have 8? No, I don't, because some of these repeat. The O repeats. So I actually only have the letter B, the letter O, the letter K, R, and M. Okay, so that's something to keep in mind. We don't have all of them. So I'm still going to go with the idea of a permutation. But the easiest way for me to do this is to just sort of write it out and explain my thinking. Since I know I have 8 letters, and if these were all different, I would have said there are 8 to choose from, and then 7 to choose from, and then 6 to choose from, etc., like we did earlier. So I'm going to start with 8 factorial. And then what I like to do for the way my brain operates is I let the denominator, each one of these factors represents a letter. This might make more sense in just a moment. Okay, how many B's do we have in the word book room? Well, we only have 1, so I'm going to start with that. This would be 1 factorial, and this represents the letter B. Okay, now remember, the numerator has all of the combination, all of them. How many O's do we have? Well, we have 1, 2, 3, 4. So what I need to do is I need to divide out the repeats. Because this is multiplication, we divide the repeats out. With what we did last time, okay, we subtracted the repeats out. So we have O, which is 4 factorial, and that's represented by the letter O. If I keep going across, I have 1K. I have 1R. And I have 1M. So I know that 1 factorial is just 1, but I just wanted to show you, this is the way it's easier for me to think about it. And so now I can simplify and say, oh, okay, that's going to be 8 times 7 times 6 times 5 times 4 factorial over 4 factorial times a whole bunch of 1s. And so now if I work that out, I end up with whatever that is, 56 times 30. Let's see. I'll clear that out. 56 times 30 gives us 1,680. Okay, so let's try another one that's similar to that, that doesn't have a whole bunch of 1s, and see if this helps. So let's do the same thing, but let's take the palindrome. Remember, a palindrome is a number or word that's the same forward and backward. So let's take the word race car. How many ways can the letters in the word race car be arranged? So again, this is a palindrome. Because it spells race car going forward and it spells race car going backward. So that's just kind of a fun little thing. All right, let's figure it out. Well, first of all, how many letters do we have? 1, 2, 3, 4, 5, 6, 7. So the natural number, the number of letters we have is 7. The counting number is 7. So that means we would have a 7 factorial, which would count all of them for the first spot, and then 6 of them for the second spot, 5 of them for the third spot, etc. But we've doubled up because we have several of the same letter. So we have to divide out the repeats. So technically we don't have to divide out by anything that's by itself, but I just do it all. So I'm going to start with R. Well, I have 2 R's. So this represents the R. I have 2 A's. I have 2 C's. And you don't have to put the 1 in, but I do. Then I've got all the letters covered, and dividing by 1 doesn't hurt anything anyway. And so this is now literally 7, 6, 5, 4. So the product of all the natural numbers less than 7. And I'm going to write it out. When in doubt, just write it out. 2 factorial, 2 times 1. 2 factorial, 2 times 1. 2 factorial, 2 times 1. 1 factorial is just 1. And now we can reduce. So if I reduce common factors. So let's see, 2 reduces with 2. And I'm going to go ahead and say 2 times 2 is the same as 4. So now I've reduced everything in the denominator except for the 1's. 1's always there. And I'm left with 7 times 6 times 5 times 3 all over 1. And I believe this comes out to be, if I've done my arithmetic correctly, it comes out to be 630. So there's 630 ways to arrange those letters in race car. Okay? All right. So that's a good example of some permutations. Now that you have the idea of how to use factorials, let's look at combinations. So I'm going to leave this up here so you can see the definition and the formula for permutation. And underneath it, I'm going to go ahead and do combinations. And remember, combinations, order did not matter. All right. All right, so number of combinations of R objects chosen, so I'm setting up the same thing, chosen from a set containing n objects. Okay, so we're going to set it up the same way, only this time it's a combination. So we want the combination of n objects chosen R at a time. And it starts off the same. As I read from left to right, I have n factorial over, and then as I read from left to right, just like I did up here, n minus r, I'm going to do the same thing. N minus r factorial. So right now they're identical, but then I'm going to multiply it by r factorial. So as I go from left to right, I get n minus r, then r factorial. Okay? So again, here we go. Let's look at a couple examples. Now we talked about earlier, if you have a committee or you're selecting a group where you might have you have like 9 people. You have 9 people sitting in a room and you want to figure out a combination of 6 of those 9. Okay, so how many ways can a committee of 6 people be chosen from a group of 9 people? Well, since we didn't say that you had to have a president, a vice president, secretary, something like that, or we didn't tell you you had to go in order from oldest to youngest or height order, since there was no order, we'll just have 9 people and you want to choose 6. So this would be a combination of 9 people chosen 6 at a time. So if I follow our formula, this would be 9 factorial over 9 minus 6 factorial, 6 factorial. That's 9 factorial over 9 minus 6 is 3 factorial times 6 factorial. And one thing to notice with a combination is if I add up these two numbers in the denominator, 6 plus 3, I should always get the 9 in the numerator. So you know you'll set it up correctly, or more than likely correctly if the sum of these two numbers is the 9. And so I'm going to expand it. I have less problems if I expand it. Now in the denominator, I notice I have 6 factorial. So I'm going to expand this as 9, 8, 7, and as soon as I get to 6 factorial, I'm going to stop. Divided by, and I'm going to put the 6 factorial there. And the other number in the denominator is 3 factorial. So I'm going to go ahead and expand 3 factorial so that I can now reduce. And so now when we reduce, 6 factorial reduces with itself. I can reduce the 3 goes into 9 3 times. 2 goes into 8 4 times. So the only thing left in the denominator is a 1, but it's always a factor of everything. So in the numerator, I'm left with a 3 times 4 times 7. And in the denominator, of course, I just have a 1. Okay? So we're left with 12 times 7, which is 84 different ways you can form a committee out of 6 people. Okay? All right. And I'm going to give you one more example. If you don't feel you need it, that's fine. We're finished. If you do want one more example, I'm going to give you one more example. Now, imagine you have a volleyball team, okay? And you have 12 members on the team, 12 players, 1 coach, and 2 managers. So we're going to have a team picture taken. And we want to know how many combinations of 7 people can be chosen to kneel in the front row. So here we go. We have a volleyball team. Consists of 12 players, 1 coach, and 2 managers. They're having a team photo taken, okay? So how many combinations of 7 people can be chosen to kneel in the front row of the team pictures? Notice it says 7 people, not 7 players, so we've got to take that entire sample set, all the people. How many combinations of 7 people can be chosen to kneel in the front row of the team picture? Okay, so the first thing we have to do is we have to figure out the number of people. So I've got 12 players. Let's see. I've got 12 players, 1 coach, and 2 managers. So when I think about how many people we have a total number of people is 15. Now the other is, when I annotate this, I see that they're asking specifically for combinations. So I automatically know I have a combination of 15 people, of which I'm going to choose 7 for the front row. So if we set this up and I read left to right, this will be 15 factorial over 15 minus 7 factorial times 7 factorial. So that leaves, I'm going to go across because I'm running out of space, 15 factorial. And again, notice when you simplify that denominator, you have an 8 factorial and a 7. And 8 plus 7 does equal 15. So I'm going to write this out and then I'll give you the answer. So I'm going to start with my 15 factorial and I'm going to keep expanding it until I get down to the largest numbered factorial in the denominator. And then I'm going to line those up because I like to just line them up. And then the other is 7 factorial. 7, 6, 5, 4, 3, 2, 1. And then we can start reducing. 8 factorial reduces. Then I'm going to start looking for some combinations. What I mean by that is, for example, 7 times 2 is 14, so that reduces. 4 times 3 is 12, so that reduces. Now what else? 5 can reduce with the 10 twice. 6 can reduce with the 9. 3 goes into 6 twice. 3 goes into 9 3 times. I think that's it. I think I have a little room left. So I'm left with 15 times 13 times 11 times 2 times 3. Oh, you know what? I could have reduced the 2. Yep, there it is. Oops. I could have reduced this 2 with this 2. Anyhow, if I multiply that all out, I got 6,435. So don't forget to put your comma in. And that's how we can use the combinations and permutations. So I tried to do a lot of examples, pretty detailed, so it ran a little longer, but hopefully this is helpful. All right, so until I see you next time, have a good rest of your day.